Welcome to my YouTube channel Neri Decoder, and today's lecture we're going to be talking about numbers and methods of numbers. Before diving into the lectures, please make sure you watch the previous lectures on JavaScript in order to follow along. Let's just dive into the lecture. In modern JavaScript, there are two types of numbers. The regular numbers in JavaScript are stored in a 64-bit format, and they're also known as double precision floating point numbers. These are numbers that we are using most of the time, and we'll talk about them in this lecture. The second type that we have are basically the big integer numbers or big int numbers to represent integers of arbitrary length. They are sometimes needed because a regular number cannot safely exceed 2 raised to the power of 53 or be less than negative of 2 raised to the power of 53. As big integers are used in few special areas, we devote them a special lecture and we'll talk about them later. So here we'll talk about the regular numbers. Let's just expand our knowledge of them. Let's talk about more ways to write a number. Imagine that we need to write 1 billion like this. The obvious way is to write it like this, but we can also use underscore as a separator. Like this. This is just for a better readability. We can also use underscore as a separator. Here the underscore plays the role of syntactic sugar. It makes the number more readable. The JavaScript engine simply ignores the underscores between the digits, so it's exactly the same 1 billion as above. In real life though, we try to avoid writing long sequences of zeros. We are too lazy for that, so we'll try to write something like 1 billion for a billion or 7.3 billion for 7,300,000,000. The same is true for most large numbers. In JavaScript, we can shorten a number by appending the letter E to it and specifying the zeros counts. So this is another way of writing it. So it's basically 1 billion, literally 1 and then 9 zeros. In simple words, or in other words, E multiplies the number by 1 with the given zeros count. So in here, E raised to the power 3 means 1000. Now let's write something very small, say 1 microsecond. Or 1/1,000,000th of a second. We can write it like this. And just like before, using the E can help. If we would like to avoid writing the zeros explicitly, we could write the same as this one, which literally means 5 zeros to the left from 1. If we count the zeros in this number, you can see there are 6 of them. So naturally it is this value. In other words, a negative number after E means a division by 1 with the given number of zeros. So the description could be -3 divided by 1 with 3 zeros could be written as this. And it simply means 1 divided by 1000, or it could be 0.001. Now let's talk about hex, binary and octal numbers. Hexadecimal numbers are widely used in JavaScript to represent colors, encode characters, and for many other things. So naturally, there exists a shorter way to write them. The binary and octal number systems are rarely used. There are only 3 numeral systems with such support. For other numeral systems, we should use the function Parse Integer, which we'll talk about in this lecture. Now let's talk about the toString method. The method number.toString with the base value returns a string representation of a number in the numeral system with the given base. For instance, let's say we have a variable called num with the value 255. I can convert this number to a string with the base 16, or I can also convert the same number to string with the given base 2. So in both cases, we'll have different results. And if we test it practically, you can see we're getting FF and also all of these bits. The common use cases for this are basically these. So the base equals 16 is used for hexadecimal colors, character encodings, etc. And the digits could be from 0 to 9 or A to F. With the base equals 2 is mostly for debugging bitwise operations. Digits can be either 0 or 1. With the base equal to 36 is the maximum. Digits can be from 0 to 9 or A to Z. The whole Latin alphabet is used to represent a number. Now let's talk about 2 dots to call a method. Let's assume that we have a number like this and we want to call a string method on this directly. And if I do something like this, let's see what it returns. You can see the error over here that says invalid or unexpected token. And when I add another dot to this and I save it, you can see that we are getting the number that has been converted to string. So what happens over here? If we want to call a method directly on a number like toString in the example, then we need to place 2 dots after it. If we place a single dot like we did before, then there would be an error because JavaScript syntax implies the decimal part after the first dot. And if we place one more dot, then the JavaScript knows that the decimal part is empty and now goes the method. Since it looks a little bit confusing, we can also do something like this. We can unwrap the number with the parenthesis, and we can use simple dot instead of using the double dots, and we'll still get the same results over here. Now let's talk about rounding a number. One of the most used operations when working with numbers is rounding. There are several built-in functions for rounding. The first method that we have is basically math.floor, and it basically rounds down a number. For example, we have a number 3.1, then it becomes 3. And let's say we have minus 1.1, then it becomes minus 2. We can call the floor method on math like this. We just have to pass the argument over here. Let's say we pass 3.1, so you can see the result is 3. Another method is called basically math.ceil. It basically rounds up a number. Let's say we have a number that's 3.1, it becomes 4. And if we have a lower number that's, let's say, minus 1.1, then it becomes minus 1. We can call the ceil method on the math constructor like this. When we pass, for example, 3.1 to this, then you can see we're getting 4. The number is rounded up. Another method that we have is basically math.round. And basically rounds the nearest integer. As you have seen in the method.floor, the number is rounded down to the lowest number. So you can see in the method.ceil that the number is rounded up to 4, since that's not the nearest one. But that is a bit different in math.round. So it will round the number to nearest integer. So we can call the round method on the math constructor like this. And if I pass 3.1 to this, you can see that it's been rounded to the nearest integer, that is basically 3. If we pass 3.6, so nearest to this number is basically 4. And if we pass the middle number, then it still goes to the higher nearest integer. Another method that we have for rounding is basically called math.trunc, and it removes anything after the decimal. So if we want to get rid of the decimal numbers at all, then we should use math.trunc. So we can call the trunc method on the math constructor like this. Let's say we have a number like this. So you can see it has been converted to 3. So all of these functions covers all the possible ways to deal with the decimal part of a number. But what if you like to round the number, for example, to a specific length or a specific digit after the decimal? For instance, let's say we have a number that's 1.2345 and we want to round it to, for example, 2 digits, and we get only 1.23. So there are basically 2 ways to do that. The first way is called multiply and divide. For example, to round the number to the second digit after the decimal, we can multiply the number by 100, call the rounding function, and then divide it back. So let's say we have a number that is basically 1.23456. Round it up to 2 digits only. We can simply call math.round. Then we have to multiply that number by 100. And at the end, we have to divide that result by 100. So if we print out the value for this, we can see that the number is rounded up to 2 digits only. What if we want to get 3 digits after the decimal? Then we can simply add another 0 to this and also to the division. And you can see it's been rounded up to 3 digits. So that is basically the multiply and divide method of rounding up your numbers. The second way of rounding your number is basically to call the toFixed method, which rounds the number to n digits after the point and returns a string representation of the result. So just keep in mind that it returns a string instead of the number. So let's assume we have this number. We need to call this toFixed method on the number, and we have to specify the number up to how much digits we want to round up our number. So on our case, I just wanted to round it up to 2 digits. I'll print it on the console and you can see that it's 1.23. But since you can see it's just a string and not a number, we can convert it to number by either adding the unary operator, or we can also use the number constructor on the number.toFixed in order to convert it to a number. Now let's talk about imprecise calculations. So internally a number is represented in 64-bit format. So there are exactly 64 bits to store a number. 52 bits of them are used to store the digits. 11 of them store the position of the decimal point. There are 0 for integer numbers and 1 bit for its sign. If a number is really huge, it may overflow the 64-bit storage and become a special numeric value that's called infinity that we talked about. So for instance, let's say we have this number, which means add 500 zeros to the 1. You can see we have the infinity result. What may be a little less obvious, but happens quite often, is the loss of precision. Let's say we have two numbers, 0.1 and I want to add 0.2 to this. So in theory, we say that it will equal 0.3. But when I make a comparison over here, you can see that we're getting false. Or I can simply elaborate it over here as well. So that is right, basically, if we check whether the sum of 0.1 or 0.2 is actually 0.3, we get false. That is strange. What is it if it is not 0.3 then? After getting rid of the comparison, you can see that it's basically 0.3 and you can see all of the zeros and it ends with 4 at the end. That's really strange. Imagine you're making an e-shopping site and the visitor puts $0.10 and $0.20 goods in their cart. The order total will be 0.30000004. That would surprise anyone. But why does this happen? A number is stored in a memory in its binary form, a sequence of bits, ones and zeros. But fractions like 0.1 and 0.2 that look simple in the decimal system are actually unending fractions in their binary form. What is basically 0.1? It is 1 divided by 10. So it looks like this. 1/10. In decimal numeral system, such numbers are easily representable. Compare it at 1/3 and it becomes an endless fraction. You can see it over here. So division by powers 10 is guaranteed to work well in a decimal system, but division by 3 is not. For the same reason in the binary numeral system, the division by powers of 2 is guaranteed to work, but 1/10 becomes an endless binary fraction. There is just no way to store exactly 0.1 or 0.2 exactly using the binary system, just like there is no way to store 1/3 as a decimal fraction. So the numeric format solves this by rounding to the nearest possible number. These rounding rules normally don't allow us to see that tiny precision loss, but it exists, and we can see that in action over here. When we sum two numbers, their precision losses add up. That's why 0.1 plus 0.2 is not exactly 0.3. Not only in JavaScript, the same issue exists in many other programming languages. For example, PHP, Java, C, Perl, Ruby give exactly the same result because they are based on that same numeric format. But can we work around the problem? Yeah, sure. The most reliable method is to round that result with the help of a method toFixed that we are just using over here. So let's assume we have these two numbers, 0.1 plus 0.2, and I'm adding them up. I can simply round these numbers, but since you can see that we are returning it as a string, then I can just add a unary operator in the beginning and it will convert it to number. Now there is a funny thing. Let's say we have a number and you can see the output, so it's really different. This suffers from the same issue, a loss of precision. There are 64 bits of the number, 52 of them can be used to store digits, but that's not enough. So the least significant digits disappears. JavaScript does not trigger an error in such events. It does its best to fit the number into the desired format, but unfortunately this number is not big enough. Let's talk about tests is finite and is not a number. Remember these two special numeric values? So infinity and negative infinity is a special numeric value that is greater, less than anything. And not a number represents an error if there is any numeric error in the mathematical operations. They belong to the type number, but are not normal numbers, so there are special functions to check for them. First function is called isNaN, which we can describe it as is not a number, and then we pass a value as an argument. So it basically converts as argument to a number and then tests it for being not a number. We can call it like this, and you can see by passing the NaN, we're getting not a number, it's true. But do we need this function? Can't we just use the comparison operator instead of this? Sorry, but the answer is no. The value NaN is unique and that it does not equal anything including itself. Let's say we add a comparison between these two NaNs, then we are getting false. Another function is called isFinite and then we pass a value argument and basically converts as argument to a number and returns true. If it is a regular number, not NaN or infinity or negative infinity. So in this case, we are calling the finite function inside the alert method and we're passing it 15 as a string and it will return true. So when I refresh the page, you can see we're getting true. So it's first convert the string into a number and then it checks if it's a finite number or infinite. And the second call, we have the isFinite function and we're passing just a string to it, so it's not basically a number. So it's basically returned false because it's a special value, not a number. And then the third call is also false because the infinity is not basically a finite number. So sometimes the isFinite method is used to validate whether a string value is a regular number or not. Now let's talk about parse integer and parse float. Numeric conversion using a plus operator or a number constructor is strict. If a value is not exactly a number, it fails. So let's say we have this value that is basically 100 pixels and is basically a string. So when I convert it to a number by adding the unary operator at the beginning, you can see that we are getting not a number, because it's a mixture of number and the letters. The sole exception is spaces at the beginning or at the end of the string, as they are ignored. But in real life, we often have values in units like 100 pixels or 12 points in CSS, if you're familiar with CSS. Also, in many countries, the currency symbol goes after the amount. So we have, for example, 19 euros or dollars or something like that, and would like to extract a number value out of that. That's what parse integer and parse float are for. They read a number from a string until they can't. In case of an error, the gathered number is returned. The function parse integer returns an integer, whilst parse float will return a floating point number. So let's say we have this number over here that is basically 100 pixels. So it will start reading this number or this string from the beginning, and until it reads the number and it finds a non-numeric value, for example the p is non-numeric value, then it will fail and it will return the gathered number, which is basically the 100. So when I save it, you can see 100 over here. And the second example, it will return 12.5 because em is not part of the number, so it will just return the 0.5, and we are applying parse float over here. But if we use parse integer instead of that, then it will just return 12. But if you apply parse integer on this string, it will just return 12. When I refresh, you can see the first value is 100 from the first alert. The second one is 12.5 because we're applying parse float on that. And in the third call, it just returned 12. What happens now when we have this case, for example, we apply the parse float on this kind of string. We have 12.3.4.5 em. You can see that it only returns 12.3 because it stops on the second point and it stops reading on after the second point it gets. There are also situations when the parse int or parse float will return not a number, and it happens when no digits could be read from the string. So you can see that the very first character here is basically not a number. So in these cases, it will return just n. When I refresh, you can see not a number in the first call and then not a number in the second call again. Let's talk about other math functions. So JavaScript has built-in math object which contains a small library of mathematical functions and constants. We'll talk about a few of them over here. The first one is basically math.random, which returns a random number from 0 to 1, not including 1. So when we call it over here, you can see that we are getting a random number. Calling it again gives us random numbers all the time. Another method that we have is basically math.max or math.minimum, which returns the greatest or smallest from the arbitrary number of arguments. So you can pass any number of arguments or arbitrary number of arguments to the math.max or math.minimum, and it will return the maximum or minimum of the list. So for instance, over here, math.max will return 5 because that's the greatest number, and math.minimum will return -10 because that's the smallest number over here. The third method is basically math.power, which returns n rise to the power of given power. So basically it will rise n to the second argument, whatever you pass it. So in here you can see math.power is 2 rise to the power 10, and it will return 1024. There are more functions and constants in the math object, including trigonometry and all that. We'll talk about in the later videos. So that is all about numbers, and I hope you have learned something new in this video. Please like and share the video, subscribe to the channel, and make sure to press the bell icon for future updates. And until then, I will see you in the next lecture.